Okay, the next topic that we're going to look at is magnetism. In this picture, you can actually see a demonstration of a magnetic field. What we have here is a current carrying wire, and the current I is going downward in the page. And basically what happened is there's some iron filings sprinkled around the wire. And when you turn on the current, these iron filings will all line up like little mini compass needles, and they will show the patterns as they line up with the magnetic fields around the wire. The fact that current carrying wires create magnetic fields was a major discovery, and we're going to talk about that later on because there's a huge amount of physics there. Now, here are magnets that people are more generally familiar with, bar magnets. And whether you've seen like a full-on bar magnet like is shown in this picture, or the little bitty magnets that you put on your refrigerator, those are the kinds of magnets that most people have more everyday experience with. Now, as you probably learned in grade school, magnets have a north pole and a south pole. And just like you get with charges, positive and negative charges, there's a force between poles of a magnet. And if you have the same kind of pole, say a north pole and a north pole, a south pole and a south pole, you're going to get a repulsive force in both of those cases. But if you have two opposite poles, a south pole and a north pole, for example, those forces are going to be attractive. And so we see like poles repel, unlike poles attract. Now, one thing that is different from the electricity case is the fact that you cannot have a single isolated pole. So, for example, if I'm talking about charges, I can have two charges. I could have a positive charge and a negative charge, and they're going to be attracting each other with some force. Well, I could take this positive charge and move it away and just have a positive charge sitting there by itself. You can't do that with magnets. You can't say cut this in half and just have a south pole and just have a north pole, because what would happen if you cut it in half is that you get two bar magnets. And so you would get something like this, where you have a south and a north, and then a south and a north. Divided again, you get additional magnets. You cannot isolate a single magnetic pole. That's a major difference between the force between charges and the force between magnets. So we see this in this slide. We can take a large bar magnet. If we break it in half or cut it in half, we don't end up with isolated south poles or north poles. You get two bar magnets. And if I cut these in half, then you get four bar magnets, each of them with their own south pole and their own north pole. Now, in this picture, we can see, again, we've placed a bar magnet around some iron filings. And what you get is you get the pattern that arises as those little iron filings act like little compass needles. They feel that magnetic force acting on them, and they line up with the magnetic field. And so that you can see that what the magnetic field from a bar magnet looks like. In fact, if you look at the drawing of the magnetic field lines, that looks remarkably similar to the field lines that you get from an electric dipole. So, for example, we might remember that if I have a positive charge and I have a negative charge, the electric field lines look something like this. They go out around. They go out like that. This is a terrible picture, but you guys get the idea. And hopefully you can see that same sort of pattern. We see that this looping around, we get the same sort of looping around with the magnetic field lines around the bar magnet. And so the fact that you get the same sort of pattern is a little bit striking. Now, there's one more feature here that's very important to realize. Now, if we consider the electric field around the electric dipole, that dipole, by the way, means two poles, just like we have a magnetic dipole right here, two poles. Anyway, the electric fields start on the positive charge and they end on the negative charge. That's the rule. For magnetism, there's a similar rule. The magnetic field lines come out of the North Pole and they terminate on the South Pole. So they start on the north and they end on the south. And so that's just something to remember. Now, the Earth itself acts like a magnet. In fact, the Earth has a relatively strong magnetic field. And we're going to talk about why that's important later on, but and also a little bit about how it's generated. But if you have a compass, the compass needle is itself a little bitty magnet, and so it's going to feel a magnetic force because we know that different magnets will either attract or repel, and the force will cause the compass needle to line up with the magnetic field. Now, what's interesting is that we know that north poles are attracted to south pole. So the north pole on the compass needle is actually attracted to the magnetic south pole of the Earth. So the pole that we normally think about as the North Pole because it's in the northern hemisphere is actually magnetically the South Pole because it attracts the North Pole of the compass needle. Now, we talked about uniform electric fields a lot when we were talking about electric fields, and we noted that if you had two parallel plates of a capacitor oppositely charged, you could get a uniform electric field. Well, if you have two wide poles, you can get a magnetic field that is uniform as well. And so we're going to see that uniform magnetic fields are also very important. They have a lot of applications, and so this is one of the ways that you can create them. Okay, here we have a demonstration of the magnetic field lines around a current carrying wire. So here you have a wire, the insulation has been stripped away, and so you have this wire that's got current going through it, and you can see compasses placed around it, and the magnetic field lines are causing the compass needles to wrap around the wire in a circular fashion. And that's actually the shape of the magnetic field lines that you get when you have a current carrying wire. So here we see the wire has a current going upwards, current I going upwards, and the magnetic field lines are circles around the wire. If I go out some distance away from the wire, I can actually determine what the magnetic field strength is there and its direction based on these loops. So for example, if I go this distance away from the wire, I could get a particular magnetic field strength there. Anywhere on that circle determined by that loop, the magnetic field strength is going to be the same value. But if I go to a different distance away from the wire, I'll have a different magnetic field strength, but it will all be the same everywhere on that circle. Now the question arises, how do I know the direction of the magnetic field in terms of the loops? Because we can see these arrows here, and we know that they tell us the direction of the magnetic field vector, which is always tangent to the field lines. So if I pick a spot here on this line, I know that that field vector is going to be tangent to that circle. And if I pick a different spot here, it's going to come out tangent to that circle. So everywhere that magnetic field vector is going to be tangent to the magnetic field lines. But how do we determine if it's going left to right or right to left? Or maybe a better way would be to say, how do we determine if the loops are going clockwise or counterclockwise? And the way that we do that is with a magnetic field right-hand rule. And now there's different types of right-hand rules that we're going to have to learn for different configurations of current and different magnetic fields. But this is the first one we're going to look at. And the rule is very simple. You wrap your fingers like a fist around the wire with your thumb extended. And so you always put your thumb in the direction of the current. So you have to know which way the current is going. How do you know that? Well, we know that, for example, if this is hooked up to a battery, the current's always going to come out of the positive terminal and go to the negative terminal. So figuring out which way the current goes is usually not a problem. So you line your thumb up with the current and you wrap your fingers around the wire, and your fingers will curl around the wire in the same direction as the magnetic fields curl around the wire. And so that's how you determine what the direction of the magnetic fields are. If somehow you knew that the magnetic fields were like this, you could do the same right-hand rule and your thumb would tell you which way the current was going. So you can use it either way. If you know the direction of the current, you can find the direction of the magnetic fields. or if you know the direction of the magnetic field lines around the wire, say for example you've got a bunch of compasses wrapped around it, then you can figure out what the direction of the current is. Now that right-hand rule that we showed you in the previous video applied to a straight wire, but it can actually work with wires in a loop as well. If you have a wire that has a current going around it in a loop, well, you can simply line your thumb up with the direction of the current and wrap your fingers around the wire, and your fingers will curl in the direction of the magnetic field loops. And so here, if you look at the magnetic field loops, you can see that they're going to be something like this. You can see this loop is going around there, there's another loop going around like that, and there's a symmetry through the loop. And so all of these different magnetic field lines are looping around the wire in this way. Being able to do this is going to be very important for us later on, because currents going around loops is one of the fundamental foundations of all of modern technology. That may seem like a bold claim, but we're going to see later on that it's absolutely true. Now, just as an FYI, I want to emphasize the fact that this is a right-hand rule. So it will not work if you use your left hand. You have to use your right-hand rule for this to work. And the other thing that you have to realize is that we are going to assume a conventional current. In other words, we're going to assume that the charges moving are positive. If you actually have negative charges that you want to deal with, you do your right-hand rule exactly the same way, and then whatever your answer is, you flip it 180 degrees. Now previously, I mentioned that there are different kinds of right-hand rules for different situations, and this is another one, determining the direction of the force on a current-carrying wire in a magnetic field, which sounds like a mouthful. Here's the basic idea. When you have moving, key word here, moving charges passing through a magnetic field, they experience a force. And that's whether you have a single charge, like a proton that's shot down a particle accelerator, or if you have a current of electrons flowing down a wire. If those charges move through a magnetic field, they feel a force. And the direction of that force is determined by a right-hand rule. And so here is an example of that for a wire carrying a current that is passing through a magnetic field. So let's look at this top situation up here. We have the positive terminal and the negative terminal indicated, so we know the current is going to be going like this, and it's passing through this uniform magnetic field. Now, remember, the magnetic field lines always go from north to south, and so the magnetic field lines are going towards the right, the current's going into the page, and we want to be able to figure out what the direction of the force is going to be. And so the rule is to make that karate chop with your thumb extended and line your fingers up with the current and then rotate them in the direction of the magnetic field. And if you do that, that will cause the thumb to point in the direction of the force. And so in this first case, if you want to apply the right-hand rule, your fingers would be pointing literally into the page, and if you're using your right hand, if you tried to curl your fingers, they would go towards the North Pole, but you want them to go towards the South Pole. That's the direction of the magnetic field lines. So if you do that, your fingers will rotate towards the magnetic field direction, and your thumb will point downward. And so the force in this situation is going to be downward. If, on the other hand, you reverse the terminals of the battery so that the current is flowing in the opposite direction, in this case, your karate chop, your fingers would literally point out of the page, and you would curl them towards the right of the screen, and your thumb would point up. So that would indicate the direction of the force. And I'm going to show this in a separate video. I'll show the physical motion of doing that so that you'll be able to see how that comes about. But the key thing here is that we have multiple right-hand rules that we have to understand how to use. And really what you need to understand is, what is the particular right-hand rule for? What is it used to calculate or to determine? And it's always going to be some kind of direction, But in the first case, we were looking at the current flowing down a wire, and the question was, what's the direction of the magnetic field created by that current? The other situation that we've now just encountered is you have a current passing through a magnetic field that's already been created, and that current is going to feel a force. So what is the direction of the force on a current passing through a magnetic field? That's going to be your second right-hand rule. Now we know that force is a vector. It has both a magnitude and a direction. And the direction is given by the right-hand rule, but the magnitude is given by this formula. The current I times the length of the wire times B, which is the magnetic field strength, times the angle between them. So let's say that we have a current that's moving from left to right, and we have a magnetic field that's going into the board. And by the way that we represent a vector going into the board, it's been a long time since we've seen this, but if you remember, you can represent a vector going into the page or into the board using x's. Conversely, a magnetic field coming out of the board is represented by dots. And so if I drew this over here on the left, that would be a magnetic field coming out of the board, but over on the right, the x's represent a magnetic field going into the board or into the page. There's a nice mnemonic to help you remember this. If you think of a vector as being indicated by some kind of arrow, well, if it's going into the board, what you see are the feathers at the end of the arrow flying away from you. But if the vector is coming out of the page, you see the tip of the arrow coming towards you as the arrow flies towards you out of the page. But let's look at this specific example here. I have a current I that is going to the right and a magnetic field that's going into the page. And what I want to determine is what is the direction of the force. Well, I'm going to line my fingers up with the current, and the current is represented by I here. I'm going to line my fingers up with the current. Remember, I've got my hand, my right hand, in the shape of that karate chop with the thumb extended, and I'm going to have the current be going to the right. I'm going to line my fingers up with that. So if I do that, my thumb's going to be pointing up. Now, if I then rotate my fingers towards the magnetic field lines, which are pointing into the board, so I'll rotate my fingers 90 degrees so that my fingers point into the page, my thumb is still going to be pointing up, and that's going to be the direction of the force. So the force is going to have a direction pointing up. How do I know that? The right-hand rule. Now, if I wanted to calculate the magnitude of the force, I would need to know what the length of the wire is. That's the L, the length of the wire. I would need to know what the magnitude of the current is and the magnetic field strength. The angle between them in this case is going to be 90 degrees. It could be something other than 90. It could be 30 degrees or 50 degrees, whatever the angle is between the magnetic field vector and the position vector pointing along the wire, the length of the wire, that is going to be the angle that we're talking about. And for those of you who have encountered the vector cross product before, this ILB sine of theta, that's the magnitude of the cross product of I times the L vector crossed into B. That just gives you that. And of course, the direction is given by, you guessed it, the right-hand rule. The same thing from the cross product that you may have seen before. But if not, you just can apply this formula. This is the formula to get the magnitude of the force vector, and the direction is determined by the right-hand rule. So let's look at another example just real quick on this page. Imagine that I have a current going up like this, and my magnetic field strength is coming out of the page. So if I lined my fingers up with the current and I had my hand palm down towards the page, if I rotated my fingers downward, that would be the wrong direction. So what I would need to do is rotate my wrist palm up so that when I rotate my fingers, they'll point along the B vectors, which we know are coming out of the page. So that is the way to do the right-hand rule for this situation. The last thing that I want to mention is that the units of the magnetic field strength are in Tesla, which are generally represented by a capital T. And we'll see that a Tesla is equal to a Newton divided by an ampere. Remember, ampere is a unit of current, and times meter. So Newton over ampere meter, that is 1 Tesla. There's also another commonly used unit for magnetism, the Gauss, and it's just a metric system thing. It's like converting from centimeters to meters, and if you have it in Gauss or in Tesla, you can convert back and forth using a conversion factor. That 1 Gauss is 10 to the minus 4 Tesla. And by the way, a Tesla is a pretty strong magnetic field. So that's why Gauss are sometimes used, because typically actual magnetic fields are going to be some small fraction of a Tesla.